Hello everyone, welcome to topic 6.9, Hess's Law. By the end of this, you should be able to represent a chemical or physical process as a sequence of steps. So this is a little bit similar to reaction mechanisms, but not quite. So the idea with Hess's Law is that we can take known chemical reactions that scientists have already studied and determined the enthalpy of reactions and add them together to get a new reaction that may not have been studied, but you could also determine by adding together different reactions, you can determine the enthalpy of reaction for a new reaction that hasn't been experimentally determined. So that's what we're going to look at in this one. So, Germain Henry Hess in 1840 discovered a very useful principle, which he named for him Hess's Law, because, scientists have that right, I guess. Hess's Law states that the enthalpy of a given chemical reaction is constant, regardless of the reaction happening in one step or many steps. So because enthalpy is based off of the energy of the products and the energy of the reactants, like the difference between those, it doesn't matter if, so we have our reaction diagram, right? Going from our reactants to our products. It doesn't matter if you take one step or a whole bunch of funky steps, the enthalpy of reaction isn't going to change. So the delta H is going to stay the same. And now that is actually called a state function, which we're going to get into right here. So in other words, if a chemical reaction, the target, can be written as the sum of other chemical equations, the enthalpy change of the target chemical equation will be equal to the sum of the enthalpy changes of other chemical equations. So if we know reactions for different steps in between, or some that could be considered steps, even if they really aren't, and we know those energy values, we can add them together to get this new reaction. And this is because Hess's Law is based on the idea that enthalpy is a state function. And while state functions are beyond the scope of AP chemistry, they are actually very important, and they do pop up, but not in their fully applied form. So state functions are important because they only begin, and it doesn't matter, there's multiple state functions. Enthalpy is only one of them. But in general, state functions don't care about the path taken from your start to your finish. They only care about where you start and end. So state functions only depend on the start and finish. Okay. Enthalpy is one of those because it only depends on the energy of what the reactants are and what the products are. It doesn't depend on how you get there, right? And that's why, like, adding a catalyst doesn't change the enthalpy of reaction either. You do drop the activation energy, but the enthalpy of reaction still stays the same. So the idea of a state function essentially means that the numerical value of a property doesn't depend on the path you take to find that value. Okay, it just depends on you actually getting to there. Okay, so these are the key ideas for Hess's Law. The reactions that we're given must add up to the target reaction. If you reverse a reaction, so you flip the reactants of products, so you change the direction, you also have to change the sign of the enthalpy for that smaller reaction. So positive becomes negative, negative becomes positive. But the magnitude or the size stays the same. If you multiply the reaction by a coefficient, and you have to do both sides so it stays the same reaction, you also multiply the enthalpy of reaction for that one. Okay? So it's kind of like a weird, very weird logic puzzle. Okay? So we're going to actually practice that here together. And quite obviously the formatting was not great when this was going on, but it's okay, we are going to make it work. Okay, so given the following reactions, calculate the enthalpy of change for the reaction below. Now, on the AP test, you guys actually can't use highlighter, but you can use an underline pen, but I'm going to use highlighter. So I'm going to say, oh, here's water. So I'm going to look for all my waters because this is going to help me make sure that they're on the right side. So then I need my nitric acid, and I could have gone back and done that one, but I'm just being weird and jumping around. Let's do this one. The nitrogen dioxide. So I have it here. And I checked, do I have it? Nope, don't have it anywhere else. And then I have nitrogen monoxide, and I have that in 2 places. So I got to pay attention for those. And those I'm probably going to wait to check until the very end to make sure that fixing the other 3 components makes that one work out. Okay. So what we're going to look at is going through each one. Is it on the right side, and does it have the right number in front of it? Okay, so our first one is nitrogen dioxide, and I see it here. Well, I see that this is a 3 and this is a 2. So I know for the first thing I need to do is I need to multiply this by 3 over 2. Okay, because that'll make this a 3. That means that I have to do the same thing here. So I'm going to multiply this one by 3 over 2. I also see that it is on the wrong side of the reaction, this nitrogen dioxide, and that's the only place it's at. So I do need to flip this reaction. Okay, so that means that I'm going to multiply this by a negative down here. So I'm going to rewrite that reaction to make sure that I'm doing it right. So I'm going to flip it. So I'm going to write my products first because they're going to become my reactants. So 3/2 times 2 is 3 nitrogen dioxides. And that is going to yield 3, because I have to distribute to everything, 3 nitrogen monoxides and 3 over 2, and we're going to hope that works out, oxygen gas. And then my delta H then becomes the negative 116 kilojoules times the negative 3/2. And I can solve that at the end. I'm not going to change that right now and try and figure it out. So I move on to the next one, and I look, okay, I see that the water is on the correct side here, and oh, that works out that the nitric acid is also on the correct side, so I'm not going to flip that reaction, but I do notice that the coefficients in the step are too big, so I am going to divide them by 2. Alternatively, if you divide by 2, that is the same as, and since I have to do it to both sides, I'm going to put the bracket, multiplying by 1/2. So I'm noting the expression the same. So over here, I'm going to multiply this one by 1/2. So I'm going to rewrite everything multiplying by 1/2. So I have nitrogen gas, N2, because 1/2 times 2 is just 1, plus 1/2 times 5 is 5/2, oxygen gas, and then adding water, running out of room, and then 1 water, and that makes 2, because 1/2 times 2 is 1 water, 1/2 times 4 is 2 nitric acids. Okay, so that means that my delta H is going to be the negative 256 kilojoules times the 1/2. And no sign change on that because I'm not flipping the reaction. Now I look at my next one. Okay, so I have nitrogen monoxide here, and I also have it here. So it's too big. If I add this 2, it gives me 5, and I only need 1. I also see that I have a lot of oxygen on my reactant side, and not quite enough to cancel it on my product side. So I'm going to flip this one, and that means I'm going to multiply this by -1, and I'm going to hope that it works out. So let's flip it and see. So 2 nitrogen monoxides are going to yield nitrogen gas. Oh, look, that's going to cancel. And oxygen gas, we're going to see if that cancels that one when we add them all together. So positive 183 kilojoules times the -1 from flipping the reaction around. Okay, so now I'm going to move this up just a little, and I'm going to see if adding this actually gives me this. So it's a great way to check your work and make sure that you've done it correctly. So I'm going to look the nitrogen dioxide. I don't have it anywhere else, so I'm just going to carry it down. And actually, I should cancel what's on both sides of the reaction, right? So nitrogen monoxide cancels one of these. So I still have one. I have nitrogen gas that cancels. Ooh, look, that goes away. And I have 3 halves plus 1 oxygen. Now 1 is the same as 2 over 2. So 3 halves plus 2 halves is 5 halves on my product side because they're on the right side of their arrows. And then I have 5 halves on the reactants. So these two together can cancel this one. And I check, I can't cancel anything else. So I'm going to bring down my reaction and make sure that what I have left matches what I should have gotten for my combined, oops, that's a liquid, my combined reaction. So NO. And we check. Granted, I did flip these two, but it is still the same reaction. So I did do it correctly. So that means that I can add all of these reactions up to get the delta H of reaction for this one. Okay. And so when I do that, I'm going to just do each individual term and then combine all 3 terms together. And you should get negative 137 kilojoules. Okay, so I just add all of these together once I multiply them to the change I made in the part above. Okay, so now we're going to try it with another problem, and I'm going to ask you guys to try first. Okay, so we are going to, you are going to use these 2 parts, these 2 reactions, to add to these 2. So you have to do a little bit of puzzling together and make sure that they work out. Okay, so we need the B, the A, the C's, and the D's here. Okay, so those are the ones that have to be in the end. So using those, manipulate by either multiplying, dividing by a coefficient, and then flipping the reaction as needed, and figure out if you can find the delta H. So please pause the video and try now. Okay, looking at this, you should see that the A or the B and the C are on the correct side of the reaction, but they are not being multiplied by the correct coefficient, so, or they need to be reduced. So I'm going to multiply these by 1/2. So that means that I'm going to multiply this by 1/2. I look at the second equation and I see that while they are the same quantity, they are not on the right side. So I'm going to flip them around, which means I'm going to multiply this by -1. And so I'm going to rewrite my equations to the right. And so 1/2 of 4 is 2b, plus 3 times 1/2 is 3 halves e, yields 2 times 1/2 is just c. That means that my delta H then should be equal to 124 kilojoules times 1/2. And I do the same with the bottom one. And I flip my reaction around, so I should get A is equal to 2D plus 3 halves E, and that my delta H should be equal to the -15 kilojoules times -1. Adding the 2 reactions together, we should see that the E's cancel, and we should get the same reaction that was asked of us, which is A plus 2B yields C plus 2D. They do indeed match, so that means that I can add my delta H to get the delta H of this reaction by combining these terms and then adding the 2 of them together, and you should get a positive 77 kilojoules for this reaction. So using this idea of weird logic puzzle, complete the You Do practice problems, check your work, and thank you for tuning in.